Hello there, this is Dr. Vivian Lowe. You're on VLMD Rounds, a podcast on medical science and tools to optimize your health. As some of you know, I started a series on atherosclerosis. I made the proposal that atherosclerosis really is an autoimmune disease. That's how we should see it, right? And in the first of the series, I talked about how LDL in its modified form, when it's oxidized or changed in any way, is now a neoantigen. Okay, so your body sees it as something not quite itself. It's a neoantigen, and really the immune reaction then is an autoimmune reaction. In the following episode, I talked about the role of cholesterol, because while cholesterol is not prime, it certainly has an important role, and that is that cholesterol metabolism really impacts and influences immune cell function and activity, right? So we can rev up the immune system or calm it down depending on which part of cholesterol metabolism we're tapping into and which immune cells we're talking about. Now, one of the fun things about starting this series is just kind of interacting with all of you. I have gotten your comments and your questions on YouTube, and it's fun to go through them and just start little conversations with you. So thank you very much, because I enjoy that, and I like to know that you're thinking about this, that this is interesting to you. So I very much treasure that. I had other topics planned in the series, and I was just going to go along my list. But then I saw this comment by a listener. Now, this is clearly a pseudonym. I'm not sure how to pronounce it. So I'm simply going to say OG. OG 6000, right? So OG wrote to me on YouTube and said, please look at Dr. Malcolm Kendrick's book, The Clot Thickens. I'd love to hear your thoughts on his theory of the development of atherosclerosis. So, as I said, I hadn't planned to do that, but when I saw that request, I thought, yeah, you know what? Sure, actually, it would be a good point to make, and it fits into this whole proposal that atherosclerosis is an autoimmune disease. So I thought, yes, why not? Let's just make an episode on that. So in this episode, I will talk about really my thoughts on the Clot Thickens, and I'll give you my perspective on it. Let's go. In his book, Dr. Kendrick basically says that it's not cholesterol and it's not LDL, but really it's the health of your glycocalyx and the endothelium, which would be the lining of your blood vessels. I did a whole episode, in-depth episode on the glycocalyx. You can look that one up, right? And basically what he's saying is that because of lifestyle factors, epigenetic factors, smoking, exposure to pollutants, bad diet, then what happens is that you degrade the glycocalyx, which is this kind of viscous lining over the endothelial cells in your blood vessel. And when you expose those endothelial cells, right, once the glycocalyx is gone or denuded, then you start to damage those cells. Those cells can be exposed to different toxins and so forth, and you can damage the cells. And when you have damaged endothelium, then what happens is that you're going to have clot formation there. And that clot formation is to, again, protect the lining of your blood vessels, kind of plug up the holes, right? And limit the wound and allow for healing to happen. So the proposal then is that it's not the cholesterol, it's not the LDL, it's really when you damage the endothelial lining and then you form a clot, and this is a blood reaction, is what I think he has been saying. All right, so there are many aspects to this, and as usual, it's a complex subject. but I'm trying to limit the episode to 30 minutes. So I only allowed myself 3 points, and I thought long and hard. And I thought, okay, so the 3 points I want to make are, number one, I want to emphasize platelets as part of the innate immune system. Number two, I want to talk about the interaction between platelets and immune cells. And number three, I am going to bring in complement. I talked about the complement system again on the episode on innate immunity. It's a pretty complicated system. I kind of went in depth a little bit over there. I'm not going to do that in this episode, but I just want you to see the link between complement and platelets. All right, so that's what we'll do. So first, let's look at how our immune system developed. So if you look at the horseshoe crab, it's known as the oldest living fossil. Kind of fascinating because it's relatively unchanged from its predecessor 500 million years ago. So the form of the horseshoe crab that we see today is kind of similar to that whole ancestral horseshoe crab, right? It's in the oldest class of arthropods. And what we've learned is that in this horseshoe crab, really there isn't a separate coagulation system and a separate immune system. It's a unified, integrated system, one system only that does both functions. So it's interesting to look at these comparative studies between invertebrates and vertebrates to see how our immune system developed. So this horseshoe crab has an open circulatory system and innate immune system. Those circulating cells, they don't have blood, so they have something called hemolymph, which is kind of their blood, but it's not the same as our blood, right? So they have these circulating cells in the hemolymph that are called hematocytes. Now, these hematocytes have pattern recognition receptors. And if you remember, these are receptors that are going to recognize conserved structures in microorganisms that may be invading, for example, or any damage or dangerous signals. Okay, they just happen to be these generic receptors that can recognize these generic patterns of danger, of invasion. All right, so these hematocytes actually have these pattern recognition receptors, and when those are engaged, then the cells know there's danger, something's wrong, and the cells are now going to degranulate because they have these granules in them, and they release the granules and form a clot. And this is so that they prevent loss of the hemolymph. They don't want to be leaking hemolymph, right? If there's any damage there. But it also allows them to trap microorganisms. So we think really that the vertebrate blood clotting system really likely evolved from this model. Now, I did a talk once called the Magical Mystery Macrophage Tour. You can still find it on YouTube. Look it up. And I looked at different macrophages. I'm going to be doing a whole episode on macrophages and atherosclerosis, so that's down the road. But you might want to look at that. In that talk, I referenced a group of macrophages. They're called the GATA6 macrophages. And these are coelom or cavity-associated macrophages. That just means that they live in different cavities in your body. So for example, the peritoneal cavity. And this would be right inside your abdomen where all the organs are. And it's bathed in this fluid, the peritoneal fluid. And in the fluid, we have all these GATA6 macrophages floating around. And they're really interesting and very helpful because they can migrate really quickly to sites of injury. And then there, they can help with defense and also repair of tissue. So we know that when there's any damage, right, inside the peritoneal cavity, very quickly those macrophages, the GATA6 macrophages, migrate there. And what do? They very rapidly form clot-like structures, very much like platelets. They just form this big clot. And this is to plug the wound and allow for healing. Now this clot formation is not through regular adhesion molecules like selectins and integrins and so forth, but rather through the scavenger receptors, right? But nonetheless, they form this clot, and the observation is like, gee, they're really acting like platelets, right? So we're starting to see that, there's some relation here between immune cells and this clotting factor, right? This ability to clot. Now, if we look at platelets themselves, platelets have a whole lot of pattern recognition receptors, right? So we think of platelets as a part of the blood system, but they have pattern recognition receptors like toll-like receptors that we see on those innate immune cells. So remember, the pattern recognition receptors can recognize PAMPs, pathogen-associated molecular patterns, or DAMPs, damage-associated molecular patterns, or danger-associated molecular patterns, right? So it doesn't just have to be a microorganism, a pathogen. Any damage or danger can be recognized by some of these pattern recognition receptors. In addition, platelets can express complement, right, which is part of the immune system, the innate immune system. And they also have the Fc gamma receptor, and this allows them to recognize immune complexes that form in the blood, right? So they can, through these receptors, recognize and bind to those immune complexes. They are also able to bind pathogens. People don't seem to realize this, but platelets have antimicrobial properties to directly kill pathogens, right? They can also aggregate when activated, and this helps them trap the microbes and in a way engulf them. Not quite phagocytosis. If you phagocytose a microbe, you're going to kill it, right? These platelets aren't going to be able to really kill those microbes by swallowing them. They don't swallow them the same way as phagocytes do, all right? And this is because platelets are very interesting in their structure. They have something called the open canalicular system, or OCS. What this means is that it really has a channel, a series of channels, right, that are contiguous with the external environment. So it kind of the membrane folds inwards and leads to these channels and little canals, right? And that's contiguous with the outside environment. And when they actually, degranulate, remember those hematocytes that would degranulate, right, in the horseshoe crab? Well, these platelets have granules too, and when they are stimulated through the pattern recognition receptors, they can degranulate and they can secrete all kinds of substances like interleukin-1, right? They can also secrete things like chemokines. And these are chemicals that are used to attract neutrophils and monocytes, other immune cells, to the area. So they also have CXCL4, for example, that they secrete. This will inhibit angiogenesis, the formation of new blood vessels. And they also activate macrophages towards a repair kind of phenotype, right? And also the CXCL4 has anti-malarial properties. So there you see that platelets are quite good at antimicrobial effects. They also release things like PDGF, platelet-derived growth factor, and also TGF-beta, so different growth factors, right? They release different substances once they degranulate. Now, I told you about how they can trap organisms and kind of engulf them. So their way of engulfing is just kind of, getting the microbe into their system or series of canals, right, into those channels there, and they hold them there and trap them in a way. And this is not really killing those microorganisms, not like the phagocytes, but it still limits their spread. And the problem with that is that if you trap the platelets, if the platelets trap these microbes in their little clot, right? These clots can still travel around in your body and spread those microbes. because those microbes aren't dead yet. So you have something like endocarditis, which is an infection of your heart valves, right? And you form these microthrombi, these microclots that can shoot out to different parts of your body, and they may be carrying some of these microorganisms that are still alive within the clot. And if they get out of the clot, then they can spread the infection, right? Now, platelets also have a lot of interaction with different immune cells. So when they have toll-like receptor activation, one of those pattern recognition receptors, right, the toll-like receptors, when they are activated that way, they can bind to neutrophils, and then they'll activate the neutrophils and help them form nets. If you remember, I talked about neutrophils and how when they self-destruct, they shoot out a web of DNA, and this will trap the microorganisms and kill them. Very toxic, that DNA, right? And that is called a net. That's what they form. And so the platelets will bind the neutrophils and help them form and make those nets to destroy those microorganisms. And we see this in liver sinusoids and also in the lungs, in the blood vessels of the lungs. So we can help trap and kill microorganisms in the bloodstream in those areas, right? They deposit fibrin and they make clots, and they again trap those microorganisms to prevent their spread. And that thrombin also can activate monocytes, right? So those phagocytes can come and attack the microorganism as well. And again, the main problem is if you're trapping the microorganisms, that's good. You're limiting the spread. You know, if you're helping the neutrophils kill them, that's great. We get rid of the microorganisms. However, if they are not actually killed but hiding in the clots, then that could be a problem. So another example, we have adenovirus type 5. It can bind to a coagulation factor called factor 10. And when it kind of binds to it, it just hitches a ride and pretends to be part of your body. So the immune system in your body doesn't recognize it. And now this virus can spread and infect the liver. Right? So it can be tricky, these little microthrombi, because it's a way to limit microorganisms, but the bad side of it is if you don't kill off the microorganism, you could help it spread to different parts of your body. And finally, platelets also help in the development and maturation of dendritic cells. These are antigen presenting cells, right? And so they're going to present antigen to your T cells and so forth to help mount an adaptive immune response. So the platelets really help in maturing these dendritic cells to do their work. Now, in the liver, it's really nice to see these platelets have a good relationship with Kupffer cells. Kupffer cells are tissue-resident macrophages in the liver. All right, so they're the main macrophages that hang out in the liver and do housekeeping properties and keep the liver safe and sound. Right now, these platelets are able to dock on top of these Kupffer cells via special receptors called GP1B receptors. I don't have to remember the name, but they have these special receptors and they dock on those Kupffer cells. And what they do is they can interact with von Willebrand factor on those macrophages, right? And basically, once they dock on the macrophages, what they do is they start to scan the surface of the macrophages, and they're looking for troublemakers, right? Do we see any PAMPs or DAMPs? Do we see any danger that's associated here? Because if we do, we're going to interact with that von Willebrand factor on the surface of the macrophages and also the liver sinusoidal endothelial cells, right? And the macrophages are going to capture the bacteria, but the adhesion of the platelets to the von Willebrand factor on the macrophages will help to encase again and trap the microorganism. And actually, if you don't have the platelets, you don't have that GP1B receptor that will attach to the von Willebrand factor, you actually see more mortality in animal studies that have been infected with organisms, right? So you actually need the interaction of both platelets and macrophages for us to be effective here in getting rid of the microorganisms. So you can see how it helps in and is part of the innate immune system. All right, the next thing I want to talk about is the complement pathway. I did go into depth in the innate immune episode. I just want to say it's a pretty complex system of proteins. And these proteins generally tend to be in an inactive form under normal circumstances, but when there's some kind of stimulus, then we're going to activate them, right? Now, we used to say that the complement proteins are produced by the liver, but it turns out that almost all cell types can make complement. So your endothelial cells can make complement, your platelets can make complement, right? Almost all cell types make complement. And this is very important because these complement proteins can attach to different biological surfaces and they become modified, right, in such a way that they become these complexes that cause a cascade reaction, right? And that cascade reaction leads to basically helping to destroy the pathogen that might be around, right? There are different stimuli to activate complement, right? We talk about the classical pathway. This pathway is activated by antibody antigen complexes. So we have a protein called C1. It's a complement protein, and it binds to these immune complexes that are circulating. Right? So that's one way, that's the classical pathway. There's a lectin pathway that binds to other chemicals, and then there's the alternative pathway. Now, with the alternative pathway, just want you to remember that that pathway is always turned on. You always have a little bit of complement activation in your body because there's always some damage in your body, right? Some cells are dying, some cells are being turned over and so forth. So any damage that is detected, we're going to activate the alternative pathway. And that damage also, by the way, just want to stress, involves damage modified LDL. Okay, so you have damage oxidized modified LDL and you can activate complement via the alternative pathway. All right, now basically this complement system kind of focuses around the C3 complement protein, and that C3 can be broken into C3A, C3B. So C3A is, it has anaphylactic and antimicrobial functions, right? So it can cause a lot of damage, and it can also be, killing the microbe. And it also will attract different immune cells to the site of inflammation. Now, you can think of the C3b as being an opsin. It really tags different damaged cells or pathogen cells, right? Microorganisms. It tags them so that phagocytes know when they see the tag, oh, this is a cell that needs to be gotten rid of, right? So it's basically helping those phagocytes identify which cells to swallow up and just get rid of completely. And as I said, you normally just have a little bit of that going on because you always have some damage, some cells that are dying that you have to clean up and get rid of. So that system is always on in your body. However, if you have ongoing inflammation, you push that inflammation on, and we exceed the limit, right? What we're going to do is push this complement system towards a different path, actually towards a further path is maybe a better way to say it, right? So we're going to push it such that we activate other complement proteins, C5 to C9, for example. Don't have to remember that. But you activate other complement proteins to form this mega, protein complex, right, that we call the membrane attack complex, or MAC, M-A-C. And the reason is that this membrane attack complex is going to punch a hole in the cell. And once you do that, it's bye-bye for the cell, right? Because it's just not going to survive that kind of damage. So when we get to that stage where it's the membrane attack complex that has been engaged, we call that the terminal pathway because it's terminal for the cell. It's bye-bye for the cell, right? So little bit of inflammation, you have that C3 going on, you kind of have a little bit of inflammation going on, but you can help kind of clear the debris that's in that area. But if you have ongoing higher levels of inflammation, then we're going to push everything towards this formation of this membrane attack complex to destroy the cell, right? The terminal pathway. Now, this complement pathway is tough because it doesn't have a negative feedback loop. In fact, it's more of a positive feedback loop, which can get you into trouble because there's no way to stop it once you start that positive feedback, right? Because it would just augment the reaction, just augment the inflammation as we go into a positive feedback loop. The way we regulate complement is actually through other mediators, other chemicals that are produced by different cells, the stromal cells, tissue cells, endothelial cells, right? These cells in the tissue can produce different factors and different chemicals that will help to inhibit the formation of this big protein complex, right? Inhibit complement activation. So we depend on this balance. We have this activation going on and it's controlled by these regulating chemicals that are secreted by surrounding cells to keep the level of inflammation sort of balanced there, right? But once we tip the balance over and we don't have enough of the regulation, then we're really going to have this mega activation of the complement system. And one thing that you should know is that part of activation of complement is really going to result in platelet aggregation, platelet clotting, right? So this is pretty well known. When you have that terminal pathway and you have that membrane attack complex, we're going to activate platelets and we're going to form more of these clots. Now, in turn, coagulation factors themselves can activate complement. So this is bidirectional. Complement activates platelets, platelets activate complement, right? It's bidirectional. So you can see that it's a very complex system here. People always think of platelets as, oh, well, they're just part of the bleeding system in your body, part of the blood. And, nobody sees that it's really very much part of the innate immune system. That's really why, the platelets are so interesting to me, okay? In fact, one of the most irritating things about the pandemic, especially the early days, and you get all these sensationalist reports in the news, and it's like, oh my God, people are getting all this coagulation happening and they're getting blood clots. What the heck is happening? And I was like, I'm part of the immune system. I don't understand why anyone's questioning this. And they're like, this is horrible. We're mysterious blood clotting. I'm like, mysterious? That's kind of Immunology 101. I mean, we all know complement activates platelets, right? And vice versa, right? So my patients would come to me and they were like very concerned. We're really afraid of this blood clotting thing. And I'm like, I hate to tell you, here's an immunology textbook and this is just part of the immune response. It's not it's really, it's not something that's only confined to this virus. If you have an immune response, you activate complement, you're going to activate platelets. So I'm not sure why that was such a big deal. And that was a huge puzzle and a huge irritation to me because every day I had to hear this rubbish going on. It's like mysterious blood clotting. And I'm like, just stop that, please. All right. Anyway, so my whole point here, I wanted to show you that the platelet itself, which is involved in clotting, obviously, is also part of the innate immune system. It has all these receptors that recognize danger, right? And the danger can involve the modified LDL, for example. Okay, but it can also recognize, remember, through it actually has complement activation, right? And when we have complement activation, complement can be activated through a number of ways. It can be activated through just simple damage that you have in your cells, but it can be activated through immune complexes. And when you have an an autoimmune effect, right? You have these antibodies binding to neoantigens. You form these immune complexes that can also activate complement, and then you will have also a clotting effect as well. So I hope that's clear that when we talk about clotting, we're not just talking about the blood, right? When you talk about clotting, you are talking about an immune response, really complex there. I mean, red blood cells, platelets, they all have pattern recognition receptors, right? So these cells are able to recognize when there's damage, when something bad's going on in the body, and they're going to respond as part of the immune response. Okay, OG, I hope that answered your question. Please let me know in the comments, and if you have further questions, then hey, why not come to my live Q&A? I will be doing it in a couple of weeks, so by then we would have talked about the neoantigen that LDL, modified LDL is, and then we would have talked about cholesterol already. We've already, just done this thing about clotting and the innate immune system. Next week, I'm going to do something I think will be equally fun. And so when I get to the live Q&A show, we'll have plenty to chat about. You can look up the schedule on my website, vivianlowmd.com. I'll leave the link in the description. And those of you who have asked how you can work with me, well, you can go to tulaversity.com, TULAVERSITY.com. I'll also leave that link in the description. And there, I will be able to help you with nutrition and with exercise and resetting your metabolic health. And also have live sessions where I can answer your questions and interact with you, just like I interact with my patients. So check that out, tulaversity.com. And I think I'm done for this episode. So signing out right now from VLMD Rounds. I'm Dr. Vivian Low, and I sing the body electric. Till next time, goodbye.